Hi, my name is Jacob Wilson, and my project is on the planets beyond ours, and it has to do with the effects of how far out a planet orbits, and how that has an effect on the mass, volume, and habitability of the planet. So first, like to start off with acknowledgements. I'd like to thank my parents, Mr. Dutton, my Aunt Whitney, the audience, and NASA and Sinbad for supplying the data. So to begin with, an exoplanet is considered to be any planet outside of our own solar system, and is the 8 or 9 planets that we all grew up to know. Most of this data came from NASA's Kepler mission, which was designed to detect exoplanets, and has exponentially increased the number of confirmed exoplanets over the years. And we do this in order to understand these planets, so we can then apply that data to our own planet, and thus the system, and so we know the properties governing our own system. And in order to find other habitable planets similar to Earth out there in the galaxy and universe as a whole. So for this project, the independent variable was orbital distance, which is measured in astronomical units, and is how far out a planet orbits from its star. I had 3 dependent variables, the first being planetary volume, second being planetary mass, and the third being habitability, or a planet's ability to hold liquid water. So my hypothesis for the mass was that the null hypothesis would be there would be no change in mass as orbit distance increased, while with the alternative hypothesis, the hypothesis was that the mass would increase with each orbital distance and then sharply decrease. With planetary volume, we have the same pattern, with the whole null being that there is no change as orbital distance changes, but volume changes as orbital distance increases, but then sharply drops off within that last increment. And with the habitability zone, the null hypothesis is that there's no change in the likelihood of a planet being habitable based on orbital distance, with the alternative being that the closer a planet is to the star, it's more likely to be habitable. So the mechanisms of why this works comes from empirical data, and data that we can see and observe within our own solar system. The pattern we observe with our solar system, we can infer onto other solar systems. And it also goes in line with the current theory of how the solar system formed, which is the nebula hypothesis, which is there was a presence of stellar dust and cloud and matter just floating in space until the cloud collapse caused by external forces. This created a spinning disk, which is the spin we see today in our system. The pressure coming from the spinning allowed for fusion, and thus creating the suns, with the process of hydrogen going to helium. And the remaining matter was clumped together to form planetesimals, and thus the planets we know today. So, due to gravity, the majority of the material would go to the sun that would be closest to the sun. That's why Mercury is so small, because the majority of that material went to the sun, while Jupiter is farther out, so it had more material for its own to become so large. However, the further away you do get from the sun, the less material there is to make a planet. That's why we have dwarf planets such as Pluto so far out. So I was able to do this project largely in part by the NASA Exoplanet Archive, which is where NASA stores all its data from the Kepler missions, and also Sinbad, which was a French database of astronomical data, which I used to get my stellar data. The Kepler Space Telescope, part of the Kepler Space Mission, is a large space telescope that orbits the Earth, and it finds a point of view. The main method it uses is the transit method, where it observes many stars at one point, and if it detects any drop in luminosity, that's most likely due to a planet orbiting it. We see this with Mercury and Venus quite often, and this is the main method for detecting planets. Others include radical velocity, timing variations, gravitational microlensing, and direct imaging, but these are not as likely to find exoplanets as the transit method. Here we see exactly how the transit method works, with the drop in luminosity occurring when the planet passes in front of the star, and then it goes back up to its usual rate. So for my data collected, the first graph we see here is mass, with the x-axis being the distance from stellar hope in astronomical units, and that mass being kilograms. However, we don't see a linear trend like we would like. It's quite flat. So I did a logarithmic transformation on the data in order to get a more accurate statistical analysis on the data and to represent it better. Here we have a line that shows a better fit, with the m being 0.2398 and giving us a p-value of 2.25 times 10 to the 10th. Again, the x-axis is distance, but in log astronomical units, while the mass is still in kilograms, but the log of kilograms. So we must keep this in mind when observing this graph. Here we see a large clump of planets. This is most likely attributed to the area, or Goldilocks zone as some people like to refer it to, where planets are most likely to form. As we move on the volume, we see kind of the same pattern we saw with the first data set of mass, where it all is clumped in the butt and we don't really get a good line. Once again, the x-axis is distance from stellar hosts in astronomical units, while the y-axis is the volume in kilograms cubed. So once again, a logarithmic transformation was ran on the data, and the x-axis is now the log of astronomical units, while the y-axis is the log of kilometers cubed. And we get a much more interesting data set, where here we see two distinct clumps, one up here and a rather large one here. This could be explained by perhaps different types of planets, such as terrestrial versus gas giant. But we can only infer and assume until we have more concrete data to do so. However, this gives us a negative slope, it would seem, of negative 0.1712, while the p-value ran with the logistic regression was 0.0094, which is significant. Now moving on to habitability. Once again, we have an x-axis of distance with measured in astronomical units. However, we see the y-axis had to be quite different. It had to be the z-score from the ideal habitability orbit, which is where the planet would have to orbit in order to contain liquid water. With the light blue planets being within the habitability zone, and that dark blue planets being outside the habitability zone. But once again, and this is zoomed in on the planets, which are right here, so we get a more in-depth look of the planets that were confirmed. And we see and it's the exact same graph, but the one is the furthest out a planet could be from its habitability zone, while the negative one is the closest it could be. And here we see some intersects to where the dark blue planets go within when they're really practically outside the habitability zone with the actual data. And this is because this all had to be averaged together and was based on standard deviations. But in the overall scheme of the data, remember, which is this, it's just minute. So a logistic transformation was performed on this data as well, giving us a graph similar to this. We can see a large clumping here when consisting of the planets outside the habitability zone, and a much smaller right here of ones within habitability zones. Once again, the x-axis is log 10 of astronomical units, while the y-axis is the z-score of the log astronomical unit. So this gave us a logistic regression was ran, giving us a p-value of 0.25125, which is not significant. 0.215, my apologies. So in summary, the orbital distance of a planet does have a significant effect on both planetary mass and volume. However, thus I reject my null hypothesis for these two. But with the habitability, the orbital distance does not have a significant effect on it. Thus I fail to reject my null hypothesis for this one. So what does this really all mean? Well, we can use this data, and hopefully when we get more data, it becomes more accurate, to locate planets with certain parameters based on their mass and volume. Thus we can find more Earth-like planets. It was also found that 6.04% of the planets are habitable, which is much higher than we believed before, and it has a great potential for finding other extraterrestrial life besides outside our own solar system. We can also draw these parallels between solar systems. Hopefully, if we're able to see these trends in our own solar system and other solar systems, we can infer they was formed the same way, based on the number of planets and once again how these systems were formed. We also do long-term case studies with Earth-like planets, such as if it underwent a process similar to climate change that we see now, which is similar to what we do with the Martian planet. And you can also draw parallels between galaxies, such as the mechanisms of how the galaxies themselves are formed and how that in turn affects the solar system formation, and fundamental differences between the planetary trends, such as will we see different trends in different galaxies based on how they were formed. So the overall message of this is that the galaxy and the universe itself is a big place. So with doing data studies like these, we can discover more about it and then understand our own being. And knowing these basic patterns and trends within solar systems, we're able to do so much more and then hopefully build a foundation for future generations. Thank you.